Today, I'm speaking with Ken Goldberg. Ken is a professor and the William S. Floyd Jr. Distinguished Chair in Engineering at UC Berkeley, a co-founder and chief scientist at robotics startups Ambi Robotics and Jacobi Robotics, and also a well-known artist.
Moravec's paradox.
Moravec's paradox can simply be summed up as what's hard for humans, like lifting heavy objects, is easy for robots. And what's easy for humans, like stacking some blocks on a table or clearing after a dinner party, is very hard for robots. Now that's the paradox, and it's been true for 35 years since Hans Moravec, who's still around, he's based in Pittsburgh, he observed this and he correctly labeled it as a paradox because it is counterintuitive, right? Why should we have this differential? But it's still true today. So the paradox itself is undeniable, I think. And but then why is this paradox is very interesting question. And you raise one possible explanation about evolution, that humans have had the benefit of millions of years of evolution. We've evolved these reactions and these sensory capabilities that are giving us that fundamental substrate that lets us perform these tasks. And you're right, and that speaking language is much more recent comparatively. And I can tell you from one perspective, let's take it from the dimensionality perspective. So this means how many degrees of freedom do you have in a system, right? So a one-dimensional system is you're just moving along a line. 2 dimensions is you're moving in a plane. And then 3 dimensions is you're moving in space. But then if you add for robots, you also have to think about, you have an object in space, you have its position in space, right? So here's my glasses, and there's a position in space, but then there's also their orientation in space.
Yep.
So that's 3 more degrees of freedom. So there's 6 degrees of freedom from an object moving in space. So that's what we typically talk about with robots. That's why robots need at least 6 joints to be able to achieve an arbitrary position and orientation in space. So that's 6 degrees of freedom. But now if you add all of the nuances, let's say of a hand with fingers, you now have maybe 20 degrees of freedom, right? So now each time you do that, you think of a higher dimensional space. And each one of those is much bigger. It grows exponentially with the number of degrees of freedom. That is an exponential. Okay, there's no doubt about it. That's a real exponential.
It exists there.
Yes.
Yep.
And so if you look at language, it's actually a beautiful example of this because it's really linear. It's one-dimensional. Language is a sequence, a string of words. And the set of words is relatively small. I mean, it's something like 20,000 words are typically used in let's say, English. And so you're now looking at combinations of all different combinations of those 20,000 words in a linear sequence. So there's many, huge, vast number, but it's much smaller than, say, the combination of motions that can occur in space, right? Because those are, there's just, it's many infinities greater than the number of sentences that can be put together.
Successes in robotics to date.
In general, what are the kind of characteristics of tasks that robots have been able to master?
Okay, good. Well, I would start by saying there's 2 areas that have been very successful for robots in the past decade. The first is quad rotors, that is drones. And that was a major set of breakthroughs that were really in the hardware and control areas, and that allowed these robots, flying robots, drones, to be able to hover stably in space. And then once you could get them to hover, you could start to control their movement very precisely. And that has been a remarkable set of developments. And now you see spectacular results of this, where if you've seen some of these drone sort of sky exhibitions, right, where they're in formations moving around in 3 dimensions, and it's incredible.
Yeah, they're incredible.
Yeah, and that has also they've been very useful for inspection and for photography. They're extremely widely used in Hollywood and in just in home sales. They're typically drones fly around and give you these aerial views. So that's been a really big development, and there's a lot of beautiful technology behind that. What another one, interestingly, is quadrupeds, which are four-legged robots. And those are the dogs like you see from Boston Dynamics, was really a pioneer there. But now there's many, many of those. And in fact, there's a Chinese company that sells one for about $2,000 on eBay, Unitree. And it's amazing because they've pretty much gotten very similar functionality. It's not as robust and smaller, more lightweight, but it has the ability to walk over very complex terrain. You can take it outside. It will climb over, rubble and things like that, in rocks and things very, very well. And it just works out of the box.
Cool.
So that was, again, a result of a number of things. It was new advances in motors and the hardware, but also in the control. And here there were a lot of nuances in being able to control the legs, and learning played a key role there. And in particular, this technique called model predictive control, which is an older technique, but had combined with deep learning, was able to address that problem and basically get these systems to be able to walk over very complex terrain and adapt. And even jump over things, and you can probably see that they can fall, roll down some stairs, and get up and keep going. So they can roll over. They can in some cases do a backflip, which is really incredible.
Why perception is a big challenge for robotics.
Perception is quite difficult with cameras. That if you even have stereo camera, you still can't really build a map of where everything is in space. It's just very difficult. And I know that sounds surprising because humans are very good at this. In fact, even with one eye, we can navigate and we can clear the dinner table. But it seems that we're building in a lot of understanding and intuition about what's happening in the world and where objects are and how they behave. But for robots, it's very difficult to get a perfectly accurate model of the world and where things are. So again, if you're going to go manipulate or grasp an object, small error in that position will maybe have your robot crash into the object, right? A glass, a delicate wine glass, and probably break it, right? So the perception and the control are both problems. And then the other one that's more subtle and I think really interesting is in physics. And the nuance there is that you can imagine just take up a pencil or pen, put it in front of you on a flat table, and then just push it with one finger forward. And what'll happen is it'll move, for a minute, and then it'll rotate away from your finger as you do it, right? Now, why does that happen? It turns out that it really depends on the very, very microscopic details of the surface of your table and the shape of your pencil. And those are essentially making contacts and breaking contacts as you're moving it along, as you're pushing it. And so the nature of those contacts is impossible to perceive because they're underneath the pencil. So by looking down, you can't see what's going on. And so you really can't predict how that pencil is going to move. So and this is an example of really an undecidable problem. I mean, it's unsolvable. And I like to say, you don't have to go into quantum physics to find very, very difficult problems that can't be, that inherently cannot be solved. Like it's not a matter of getting better sensors or better physics models, but we just can never predict that. We'll never be able to, because it depends on these conditions which we can't perceive. So we have to find ways to compensate for these, all three of these factors, which is the control errors, the perception errors, and the physics errors, call it. And those humans do it. We have an existence proof. We know it can be done. And humans have the same limitations, Right. So how do we do it? And that's the $1 million question or $1 billion question.
Yeah. No kidding. Yeah. Well, that made me want to ask, you said it's an unsolvable problem. And maybe I'm just kind of misunderstanding, but do you mean that it's unsolvable with the perception we have now for robotics? Because I don't know exactly kind of where the pencil I push on the table is going to end up, but I do manipulate pencils and make pretty good predictions about what would happen if I, nudged it forward.
Mm-hmm. Yeah. So you do. But you can't, what I mean is that you cannot predict exactly where that pencil is going to move if you start to push it.
So humans can't do it as well, this thing that you're talking about.
Right. No one can. I'm saying that no model in the universe can solve this problem because it depends on what's happening at the really almost submicroscopic level that is basically going to influence how that pencil responds to being pushed. And it's friction, but in a very nuanced way. And, in friction, we have this model we all learn in college or in high school called Coulomb friction. And it's a reasonable approximation, but it's a rough approximation to the real world. And it doesn't really describe what happens when you push an object across a surface, how it's going to move. And so that this is known to be a very, very nuanced and subtle problem. And it's right in front of us. And you're right, we solve it. When I want to say solve it means not predict it exactly. What we do is we compensate for the error.
Right.
By the scooping kind of motion, where we move our fingers in a way around the object. And we have a word for that. We call it caging, which is caging. Caging is where you put your fingers around an object in such a way that it is caged, meaning that it can't escape. So it can move around, it can rattle around inside that cage, but it can't get out of the cage. So once you put your fingers in a cage around the object, now you start to close your fingers. Well, there's nowhere for the object to go. So
Right.
It generally will end up you'll be able to pick it up.
Why low fault tolerance makes some skills extra hard to automate.
Why do you think we won't have fully autonomous robot surgeons in the next 30, 40 years?
Okay, so the issue here is fault tolerance. And this is where, and I'm glad you brought it up, because this is why self-driving cars are particularly complicated and challenging, because they're prone to a small fault, a small error could be quite disastrous, right, as you know. And you could, if you're driving on a cliff, small error and you go over the side, or you bump into a stroller or run over a kid. So driving is very challenging because of that. In contrast to logistics, because in logistics, you drop a package, it's no big deal. In fact, it happens all the time. In fact, they expect it to happen a fairly large amount of time.
Mm-hmm.
So something like 1% of packages gets dropped. It's okay. That's not a big deal. So you can live with it. But in driving is not very fault tolerant. In surgery, even less. So you have to be really careful because you don't want to puncture an organ or something, or sew two things together that shouldn't be sewn together, right? So there's a huge consequence. The other thing, Luisa, is perception, because now you have inside the body, you have, it's very challenging because there you have a lot of, oftentimes there's blood. Or if it's a laparoscopic surgery, you're constantly essentially trying to avoid the blood and staunch out the blood so that you can see what's going on. And this is where, just as you were describing watching a robot, someone crack an egg, surgeons have developed this really good intuition because they know what the organs are, they know what they should look like, how they're positioned, and how thick or rough or their surfaces and their materials are. So they have very good intuition behind that. So they can operate. Sometimes there's you cut a blood vessel and the whole volume fills with blood. And now you have to find that blood vessel and clamp it so that you can stop the blood. And that's like you reaching into a sink filled with murky water and finding the thing, right? So And surgeons are very good at that, right? And it's a lot of nuance. So the perception problem is extremely difficult because everything is deformable. Materials are particularly difficult for robots. So, we talked about cracking an egg or clearing a dinner table. Generally, all those objects are rigid. But when you start getting into deformable things like cables or fabrics or bags or a human body, right now all of a sudden everything is kind of just bending and movable in very, very complex ways. And that's very hard to model, simulate, or perceive.
Right. Yeah. I'm just finding it fascinating, the categories of things that are really, really troublesome, thorny problems for robots are just not what I'd expect. I mean, the fact that you can, we're making progress on suturing, but it gets really complicated as soon as an organ, you could move it and it would, it's hard to predict how it's going to look when it moves or where it's going to be, is just, it's just unexpected and really interesting.
Absolutely. And I think, I'm just, as you're saying this, I'm thinking of going back to the kitchen, kitchen workers in restaurants. So much nuance going on there. If you're chopping vegetables or you're, unpacking things out of a, let's say, every single chicken breast is slightly different, right? And so being able to manipulate those kind of things and then clean surfaces and wipe things and stir and all, there's so many complex nuances. So I think it's going to be a long time before we have a really fully automated kitchen, systems. And the same is true for plumbers and carpenters, electricians, anyone who's basically doing these kind of manual tasks, fixing a car. They're very, very require a vast amount of nuance. And so those jobs are going to be very difficult to automate.
How might robot labor affect the job market?
So here's where I also think there's a huge amount of fear out there, and it's really important to reassure workers that this is not imminent and that what they do is very valuable and safe from automation. I think everyone's been saying for years that we're going to have factories, lights out factories, and that humans will just sit around and have all this leisure time, maybe even like Wall-E or something, right? But no, it's not. We're very far from that. And the fact is that there's so many nuances to what humans do in jobs. And, AI is a whole realm of office workers and what they do. And I think that there's certainly many aspects of jobs that can be automated. And, for example, transcribing this interview is a perfect example where in the past it had to be done by a human. Now you get a machine to do most of it. Then you tune it. You still have to fine tune it, but you get a lot of the basic elements done. So right, we have a lot of tools that make certain aspects of our job. But then what we do is we spend more time, because every other aspect of our job needs more attention than we have, so we can spend time on that, right? So same is true for so many of these things we're talking about. So gardeners, et cetera, there will be need for, there'll still be a need for the gardener to be doing the more subtle things, but maybe some machine will be out there and, doing the lawn, right? We're getting closer to automated lawnmowers. And so for workers, I think, certain things in the kitchen may be automated. And obviously we have dishwashers. We have certain automation already we've had for a long time. So, but that doesn't mean we don't need human workers. And so I think we're going to need them for things that are much more subtle. And so I'm sort of optimistic about the job market. I think that, because of this demographic thing, that's the biggest factor, which is that we have a shortage of human workers, people who are of work age. And so I don't think, there's going to be this kind of unemployment that people are talking about or fearing for a foreseeable future.
Yeah. If in, I don't know, let's say 10, 20 years, robots are super widespread and are causing real job displacement. What do you think played out differently to how you expected?
Well, okay, so let's say one of these breakthroughs we're talking about happens, and all of a sudden then robots are capable of learning from YouTube videos and then repeating anything they watch. Or maybe you demonstrate, this is how I want to, chop these vegetables, and now it's able to repeat that reliably. So if we got those breakthroughs, then you could imagine that you'd have these robots. Another factor we haven't even touched on, which is not as interesting, but just the cost, the financials of doing these, right? So, but let's say that gets finessed too. So now all of a sudden you have these robots, and they're actually pretty capable, and we're seeing them, increasingly being put to use and actually doing something useful. Then I think it will be interesting. I think that would change our perceptions of them. My own sense is that we would find new work for humans to do, that we would basically shift toward other things that are more subtle. Like, let's say, maybe it's healthcare and things like that, right? We have shortage of humans that can do those things, and also teaching and childcare. And there's a lot of things we are just still shorthanded. So I think that people will find new jobs, but some of these things might be automated. But I guess the extreme form of this is that you have a robot that can do anything that a human can do, and you just have them doing it all. And then what? So we hang out, we can spend time playing music and writing poetry and doing all the fun stuff. And it's an interesting prospect.
Yeah.
Right? I mean, maybe we'll drive ourselves crazy because we'll have so much free time,